Hello everyone. So in this video, I'm going to cover few of the important topics of chemistry, not in much detail, but it will be a sort of revision video of the major important topics. So without delay, let's get started. So let's say if somebody asks you to calculate the number of optically active optically active isomers of a given compound, let's say isoleucine or glycine is itself optically inactive, so this formula is not for glycine because glycine do not have optically active or chiral carbons. So the formula is 2 to the power n, where n is the number of chiral carbons. Chiral carbons or asymmetrically active carbon. Asymmetrical carbons. Okay. So if they will ask you about the this is 2n minus 1. Okay, so if they simply ask you the number of optical isomers, then it will be 2 to the power n. If they will ask you optically active isomers, then it is 2 to the power n minus 1. If only optical isomers, then 2 to the power n. Okay, and then this is very basic. The atomic number of an atom is equal to the number of protons in that particular atom, and if the atom is neutral, then it is also equal to the number of electrons in the atom. Okay. Then if I'll talk about atomic mass, then it is equal to the sum of number of protons and the number of neutrons in the particular atom. Okay, this formula is pretty important. Energy of the photon in an electromagnetic wave or the radiation is h nu, where nu is the wavelength. Nu is the wavelength, E is the energy of the photon, and H is the Planck's constant. Okay. And there is one more thing, that is wavelength of the wave to which this photon belongs. There is a relationship between frequency and wavelength. C is equal to nu lambda, where nu is equal to C upon lambda, or you can say lambda is equal to C upon nu. This is C, and the C is the velocity of light in vacuum. Okay. And its value is 3 into 10 to the power 8 meter per second. Okay. Moving on to the next topic. Okay. So there is like EM spectrum. You just have to remember this in order, because in sometimes they ask to find the correct option in which they have arranged these waves in a increasing order of wavelength, increasing order of frequency, or vice versa. So first of all, there will be gamma rays, then X rays, UV rays, visible rays, and invisible rays VIBGYOR. Red will have more wavelength than violet. Visible rays, then infrared rays, then microwaves, then radio waves. Okay, so when we'll move from this side to this side, the wavelength increases. And since we know that C is equal to nu lambda, means nu is equal to C upon lambda, means nu is inversely proportional to lambda. So whenever wavelength increases, frequency decreases. So if frequency decreases, E is equal to h nu. If frequency increases, energy increases. Okay. So when we move from left to right, the frequency decreases and energy also decreases. Okay, so it means a photon belonging to red light will have more wavelength, less frequency than this violet, and lesser energy. Just a minute. Okay, so yeah, if there is one more formula for the wave number, that is 1 upon lambda 109677, 1 upon n1 square minus 1 upon n2 square per centimeter. So what is n1 and n2? It is the shell numbers. So if an electron moves from n1 shell to n2 shell, so this is gonna be the wave number of the light emitted or absorbed by the electron when it moves from one shell to another. Okay, so for Balmer series, the value of n1 is 1 and n2 can be 2 to 3 infinity. And it belongs to UV range. For Lyman series, from 2 to 3, 4, and so on up to infinity, it belongs to visible region. Balmer, sorry, I have written the other way around. This is like here Lyman will come and here Balmer will come. So Balmer belongs to visible range and Lyman belongs to UV range. Sorry. And then is the Paschen, bracket series, fund series. 3, 4, 5, and it will go from 4 to infinity. It will go from 5 to infinity and 6 to infinity. And these all belongs to infrared region. Okay. So if they will ask you about, uh, if they will ask you to calculate the energy of an electron present in some shell, let's say first shell or the second shell or the third shell. So if you know the shell number and the atomic number of the atom to which electron belongs, Z is the atomic number and N is the shell number. So then the formula to calculate the energy of the electron in a particular shell and atom, the formula for this is 13.6 Z square upon N square, and this value will be in electron volt. So one electron volt is 1.602 into 10 to the power minus 19 joule. It means joule is a bigger unit of energy than electron. Okay, let's move on to the next thing. And if they ask you to calculate the radius of the shell in which the electron is, then the formula is 52.9 n square upon z. The value will be in picometer. If you have to calculate it into meter or centimeter or something, I have already taught this in the last physics one shot video. Okay. And there is a relation between the angular momentum. Angular momentum is equal to mvr, where m is the mass, v is the linear velocity, r is the radius in which the electron is. This belongs to nh by 2 pi, where h is the Planck's constant, n is the shell number 1, 2, 3, whichever shell it belongs to, and 2 pi. And this relation is important. That is the de Broglie relation. De Broglie relation is between the wavelength and linear momentum. This is h, that is Planck's constant, and this is linear momentum. So h upon mv. Right. Let me tell you the value of Planck's constant, that is 6.626 into 10 to the power minus 34 joule second. 1 minute. Okay, great. Yeah, there is a relationship between the kinetic energy of the electron and the linear momentum. That is, this is P is the linear momentum. The formula for linear momentum is mass into velocity. Similarly, for the angular momentum, L is the angular momentum. This is P into R, where P is mv and R. Okay. Let me tell you a bit about the quantum numbers. So N is the principal quantum number. Its value starts from 1. First shell, second shell, third shell, fourth shell. People will also call it as K, L, M, and N. Okay. Let's talk about the angular momentum number. If it belongs to S subshell. You know, na, there are S, P, D, F subshells. So S, P, D, and F. If the electron is in S subshell, then the angular momentum number will be zero. Everywhere. S zero. If it is in S subshell, then the angular momentum number will be zero. If it is in P, then 1, 2, and 3. So, okay. And the spin quantum number is also always plus half and minus half. Okay. If you have to find the number of angular nodes, then it is equal to the angular quantum number. And if you have to find the number of radial nodes, then it is equal to n minus l minus 1. And if you have to find the total nodes, then it is n minus 1, where n is the this principal quantum number. Okay. So let's talk about periodicity. I hope you know few of the like you remember the few of the members in series in a particular group. Let's say group number 1. You should remember this group number 1, group number 2, group number 13, 14, 15, and 16. It's good to remember. Okay. So if we go from left to right along a period or top to bottom down a group. Okay. So what happens is atomic size. When we go from left to right, atomic size decreases. And when we move from top to bottom, atomic size increases. Now, ionization energy. What is ionization energy? Name suggests when we make atom and ion. So whenever we have to make an atom ion, so we are asking for electron, we have to give energy. So the amount of energy that should be given to atom to convert it into an ion, then this is what we call ionization energy. So more the size of the atom, farther the electron is from nucleus, lesser will be the attraction, means lesser energy you can give to extract the electron and convert the atom to ion. So as we go from left to right, atomic size is decreasing. So ionization energy is increasing. And when we move from top to bottom, atomic size increases and ionization energy decreases. Okay. Now there is one more thing, that is electron gain enthalpy. This is different. This is like when you want to give electron to a atom. Electron gain enthalpy. So if the electron is willing to take the electron, the atom will give off energy. Okay. But if the atom is not willing to take electron, but you want to give them electron, then the energy you have to give extra. You got my point. I will explain it with the example, then you can understand it better. So let's say there is chlorine. Chlorine have 7 electrons in its outermost shell. It needs one more electron to complete its octets. Okay. So the electron gain enthalpy for halogen, that is chlorine, is negative, highly negative. Means it will, like when you give a electron to a chlorine atom, it will be happy because it has completed its octet, so it will give off energy. So electron gain enthalpy will be negative for chlorine. Let's talk about noble gases now. Noble gases, let's say argon. Argon, it has already completed its octet. It do not need more electron, right? But you want to give it electron. It is not willing to take. So you have to give extra energy if you still want to give electron to argon. So for him, no, not for him, for it, the electron gain enthalpy is positive. So when you go from left to right, the electron gain enthalpy becomes negative. You can say it less. And when we go from top to bottom, electron gain enthalpy increases. Okay. Uh, there is one more thing, that is electronegativity. It is a fancy term given to non-metallic characters. So as we already know in the periodic table, when we go from left to right, the non-metallic characters increases because here are metals, here are non-metals. So electronegativity increases. When we go from top to bottom, the electronegativity decreases because metallic characters increases. Okay, great. Let's talk about this. Um, just a minute. I would just want to tell you this thing. Shielding is directly proportional to the atomic size. Shielding is nothing. It's like there are electrons in this shell, there are electrons in outer shell. So outer, the electron which is more closer to the nucleus feels more attractive force than the outer electron in the outermost shell. So this effect is shielding, means these electrons are shielding the electrons in the outer shell to feel the attraction of the nucleus. So this is what we call shielding effect. More the greater the size of the atom, greater will be the shielding effect. Okay, now let's talk about bonding. So there is one thing that is bond order. Bond order means the number of bonds in a particular compound. So let's say if there is one bond, means the strength is less. If two bonds, strength is more. Three bonds, even more strength. So bond order, when bond order increases, the strength of the bond increases and the bond length decreases. Because if the strength is increasing, means the atoms are more closer, right? I hope you got it. So there is one more term that is isoelectronic species. Isoelectronic species means the species which have same number of electrons. Okay. Now let's talk about hybridization. If the hybridization is sp, then the angle will be 180 degree and the geometry will be linear as in case of carbon dioxide. And example is BeCl2, carbon dioxide. If it is sp2, then this is 120 degree and trigonal planar. For example, BF3, BCl3. Okay, for sp3, let me write down it quickly. sp3d2. For sp3, angles are 109.5 degree and the shape is tetrahedral as is for water, for methane also. Oh, water is not having tetrahedral. Water is not having tetrahedral. Okay, 120 degree. Three bonds in this, like PCl5, example is PCl5. Three chlorine atoms are in single plane. So their angle is 120 degree. And one chlorine is above and one is below. So 90 degree. Two bonds are having 90-degree angle and three bonds are having 120-degree angle. So this shape is called trigonal bipyramidal. This shape which I have drawn now. Okay. For sp3d2, all are 90 degree. And the shape is tetrahedral. Example is SF6. Okay, let's quickly move on to the next thing. Okay. Mm, what is this? So if we found out that the hybridization of a particular compound is sp3d, what will be its shape? As I have already shown you in the previous table, sp3 is trigonal bipyramidal. And there is a theory named Weisshauper theory. What it says is lone pair interaction is more than lone pair bond pair interaction than bond pair interaction. So what is lone pair? What is bond pair? Let me tell you. Uh, like in the oxygen, there are these electrons, six electrons, na? So when oxygen make bonds with two electrons, the excessive electrons which are left out are termed as lone pairs. Lonely, akele, lone pairs. Okay. So how we find the number of lone pairs? That that is total number of electrons in the outermost shell minus the electrons which are participating in bond formation. Okay. And there is one more relation, that is bond angle is inversely proportional to the number of lone pairs. For example, if there is no lone pair, then the angle will be 109.5 degree. If one lone pair is there, then the angle will be 107. And if two lone pairs are there, then the angle will be 104. Great. Just a minute. Okay. Now this is a bit important. For oxygen, you must remember the bond orders. Let's say if in the this is not particularly for oxygen only. This is for this is pretty much applicable to all compounds. So let's say if the number of electrons are 10, it can be 11, 12, 13, 14, 15, 16, 17, and 18. Then bond order. If the number of electrons are 10, the bond order is 1. If it's 11, it's 1.5. Then it is 2. For example, for carbon. Sorry. Yeah, it is 2.5, 3, let's say for nitrogen. Because it's 14, na? Atomic, atomic number. That is the number of total electrons. Then again it start decreasing. 2.5 to 1.5, 1. Okay. If I have to find the dipole moment of a particular atom or compound, sorry, then it will be charge multiplied by the distance. These things will be given. You just have to remember it. They can give you distance, dipole moment, and they might call you to calculate the charge. You just have to remember this. And there is one more thing, that is magnetic moment. Magnetic moment is equal to under root of n into n plus 2. What is n? N is the number of unpaired electrons. Okay. Now let's move on to the chemical kinetics portion. This is pretty much important. You might expect at least one question from this part. Okay, let me first tell you about the order, how you have to calculate the order. So let's say there is a rate equation. A plus B is moving to C plus D. Then what is the rate? Rate is the change in, let's say if there are A moles. So this is reactant. So change in concentration of A, since there are A moles, so it will be -1, because it is being consumed, na? So it will be 1 A mole, so 1 by A, because it is a reactant, it is being consumed, so minus change in concentration of A. This is a rate, okay? And also we can write the rate order equation like this. It to B. So let's say if it is B, then A to the power A, B to the power B. A and B are the number of moles, okay? And if I have to find the order, that will be A plus B. Order is the sum of these powers in the rate law equation. And this is K, which is a constant. It depends upon the temperature conditions. Only temperature. Okay. For zero order reaction, what happens is, this is the concentration of the reactant and this is the rate. No matter what, R is equal to A to the power 0. No matter what, how much concentration you will increase, rate is gonna same. So this will be the graph. And for the first order reaction is super important. For first order reaction, what happens is, when you increase the concentration of A, because R is equal to K, A to the power 1, as you increase the A, rate also increases. So it is a linear dependency. And for second order, it's this exponential. Sorry, second order parabola. This is not exponential. Okay. Now I will write down the formulas. You please remember all these formulas because you can at least expect one question, especially from the first order. Okay. For zero order reaction, let's say A is the initial concentration and later on A final. A, like, after the reaction is completed, AF is the final concentration of the reactant left. So how you will calculate the rate constant and all these things? This is the relationship. After time t, let's say 20 minutes, 40 minutes, or whatever. This is the initial concentration when you started, when t is equal to 0, and then t is equal to t, then kt. K is the rate constant. Great. If you have to find the half-life of zero order reaction, then it is initial concentration of A divided by 2K, where K is the rate constant. Okay. Now, it's the term for first order. What is for the first order? K is equal to 2.303 by T log of A naught by A. Or you can also use this formula, natural log of A naught by A. This is the initial concentration, final concentration, 1 by T multiplied. So it's better to use this formula always. Calculator will be there, you will be easily able to follow this. This formula is super important. Okay, if you want to calculate the half-life of a compound in following a first order reaction, then it is 0.693 by K. Okay, there is one more equation, Arrhenius equation, that is something related to the activation energy. Rate constant is equal to Arrhenius constant e to the power EA by RT. R is the gas constant, universal gas constant, T is the temperature conditions, A is the Arrhenius constant, and EA is the activation energy for the reaction. Okay, let's move on to the equilibrium now. For equilibrium constant at constant pressure is equal to equilibrium at constant concentration, RT to the power del N. What is del N? This is the change in the number of gas moles. Okay. So if we will increase the concentration, then the forward reaction will increase. If we increase the react concentration of products, then the backward reaction will increase. Now, this is also important in terms of, let's say, for thermodynamics. Oh, I forgot to mention one formula. This is very important formula. Gives free energy is equal to give standard gives free energy plus RT natural log of Q, where Q is equal to K when delta G is equal to 0. Okay. Uh, this is pretty much important. This is equilibrium constant. Kc, most of the time it is Kc. And you can calculate this Kc as the product ka concentration divided by reactants concentration. You can expect one question from this. Okay. Now let's talk about Boyle's law. What Boyle's law says is pressure P1 V1 is equal to P2 V2. Means when you increase the pressure, volume will decrease. And there is one more law, that is Charles' law, which says volume is directly proportional to temperature. When you increase the temperature of a gas, it will expand because it will have more kinetic energy. So it's like V1 by T1 is equal to V2 by T2. And there is one more law, Gall-Lussac's law, which says pressure is directly proportional to temperature, means P1 by T1 is equal to P2 by T2. And combining all these, there is a Okay, there is one more law, that is Avogadro law, which says volume is directly proportional to the number of moles. More the number of moles, more will be the volume. Okay. Now you should remember this equation. PV is equal to nRT. This is super important. Pressure, volume, number of moles, universal gas constant, temperature. Okay. Now this delta U is equal to work done plus heat provided. This, what is this? Change in internal energy. Change in internal energy of a system is the sum of work done on the system and heat supplied to the system. If it is supplied, then it is plus. If it is taken out, then it is negative. If work is done on the system, it's positive. If taken work done by the system is negative. Okay. And work done is equal to pressure, negative pressure, change in volume. That is PV. Okay. And delta H is enthalpy is equal to change in internal energy plus PdV. These are sort of you should keep in mind. And also one thing, Cp minus Cv is equal to Nr, where R is the gas constant. Cp is the specific heat at constant pressure, specific heat at constant volume. Okay. There is one more important equation, that is Helmholtz equation, Gibbs Helmholtz equation, that is delta G is equal to delta H minus T delta S, where delta G is the free energy change, free enthalpy change, not free enthalpy change. T is the temperature and S is the entropy change. This is also important. Okay, now let's move on to the electrochemistry. This is going to be the last thing. Chemistry, electrochemistry. So, electrode potential is equal to standard electrode potential at cathode minus standard electrode potential at anode. So, cathode reduction happens and at anode oxidation happens. Oxidation is the loss of electrons. Reduction is gain of electrons. Okay, now I will write a single equation, not single, there will be two equations. Minus NF E naught of cell. If there is, this is the relationship between free energy and the electrode potential. And this is the number of electrons, and this F is the Faraday's constant. Its value is 96500. So 96500 Coulomb is for 1 mole of electrons. So N is a moles of electrons. Great. So one thing more, if delta G is equal to 0, means the equation reaction is at equilibrium or the process. When it is negative, then the process is spontaneous. And if it is positive, then it's non-spontaneous. Okay. Now final equation, last equation, that is electrode potential at particular condition is equal to electrode potential at standard conditions, that you can calculate E cathode minus E anode, na? Minus RT universal gas constant, temperature, N and F. I have already explained these. Anode, moles of ions at anode and moles of ions at cathode. Molar concentration, which is basically molar concentration. Or since R and T are, these are standard conditions, like temperature is 25 degrees and this is universal gas constant and F is also constant. So for standard condition, you can write this 0.059 upon N natural log of a naught by thought. Okay. And there is a relationship between this E naught cell and because it's zero at equilibrium, then it will be 0.09 log Kc. Kc is the equilibrium constant. Now let me tell you about the molar conductance. The formula for molar conductivity is 100 into, sorry, 1000 into kappa upon C, where this kappa is specific conductance. They will give the value if they will give the value of specific conductance if they will ask you to calculate the molar conductance. Okay, then if you have to calculate the degree of dissociation, then it will be lambda n upon like molar conductivity at the particular temperature conditions, molar conductivity and standard conditions. This is degree of dissociation. Now let me quickly discuss about pH and buffers. Okay, before that, I would like to tell you about this formula. This is absorbance for spectrometry, na? This is molar extinction coefficient. This is the concentration. This is the path length. And path length is mostly 1. And they usually ask you that, let's say for a DNA, the absorbance was 1.3 or something, and the molar extinction coefficient is, let's say, 5, and find the concentration. So you will write C as L as 1 centimeter always. And for concentration, what you will do? A divided by this. This is what molar extinction coefficient. They will give its value. If it is in meter, then you have to use 10 to the power minus 2 in place of 1 centimeter. Because if the units of this molar extinction coefficient are in centimeter, then you will use 1 centimeter only. But if it is in meter, then you should convert this in centimeter into meter. No? Okay. And also this absorbance is equal to log of initial intensity of the light which we put it on the sample divided by the final one which is coming out of the sample. And also absorbance is equal to negative log of transmittance, and it's most always an integer value. Absorbance is equal to 2 minus log of t. This is in the percentage. For average half-life and all these things, if nothing is given, you should consider first order reaction only. And for microbial kinetics, this will follow. Even for the like half-life of a particular compound, not compound, for atom, if they will say decay constant is this and all, so decay constant is equal to this the K which we used in the equation, na? Rate constant. That rate constant will become decay constant, otherwise every formula will be same. Okay. Let me see if something is left. I have already put these notes in the Telegram channel. You can have a look on these notes. Okay, so let's end this video here. And there is one more equation, Henderson-Hasselbalch equation. Please look upon this. Henderson-Hasselbalch equation. And with this note, I would like to end this video. So thank you so much for joining.